This is the practice test for chapter 11, 12, and 13. Number 1, the main forces responsible for holding potassium bromide together. Potassium, remember, is a metal. Bromine is a nonmetal. So potassium bromide would be an ionically bonded together thing. And so you'd say ionic bonds. Remember, ionic bonds are an intramolecular force between the ions, and then they'd form a crystal lattice that holds those together, and they're super strong. Number 2, which of the following has the lowest boiling point? So now you want to take a look at the types of substances and notice that these are all nonmetals, and all nonmetals then are held together molecularly by intermolecular forces. And the intermolecular forces that you should be really familiar with are London dispersion forces, dipole-dipole forces, and hydrogen bonding forces. And of these right here, you'll notice that every single one of these has no polarity to it and no hydrogen bonds to it because they're all perfectly symmetrical. So these types of forces don't apply. If you aren't sure what kind of forces are together, the steps you should take is to draw the Lewis dot structures of them, or at least a rough draft of them. And so for A, if you draw a rough draft Lewis dot structure, it's CH4. For B, it's C3H8. It's going to be symmetrical. I won't draw all the hydrogens in there. For letter C, it's C5, and then there'll be 12 H's around there, just like that. And then for D, it will be C4, so 4 in a row, and there will be 10 H's around there. And then for the last one, N2, that'll just be a nitrogen to a nitrogen. But you'll notice every single one of them is perfectly symmetrical like this. And if it's perfectly symmetrical, you can cut it any way, and it's the same on both sides. That means that the only forces that hold it together are London dispersion forces. Remember, if it's asymmetrical, that means that we'll have dipole-dipole forces, or the fancy name for that type of molecule is a polar molecule because it has more than one pole. So if you look at these, the only thing that governs them are London dispersion forces, and those are decided by the number of electrons in the molecule. And so if you look at this guy right here, it has 6 electrons for carbon, 1 for each hydrogen, so a total of 10 electrons. And that's going to end up being like the least number of electrons. And then this nitrogen right here ends up having, I believe, 7 and 7, so about 14 electrons. Those two are your smallest ones, and those will end up being the ones that would have the lowest boiling or lowest melting point. And so the opposite would be true then, the one with the, oh, I'm sorry, it asked for the lowest boiling point. I was reading number 3. The lowest boiling point then would be the one with technically either the least electrons, so one of these two right here, and as it turns out experimentally, this one ends up having the little bit lower boiling point. And the reason for that is because this one is such a small surface area molecule compared to this one that the hydrogens go a little bit further apart. So
how would we know that?
This actually is a super tough question because you can narrow it down to these two, but the reason that you know that this one would have a little bit lower boiling point, it actually separates like the 4s and the 5s on an AP exam, and the difference comes down to what's called surface area. And the greater the surface area, the more opportunities that those electrons have to do what's called instantaneously polarize or form these London dispersion forces. And since these hydrogens stick out from the carbon and make it just a little bit bigger surface area wise, rather than just 2 atoms stuck together, it will give you a little bit more surface area and actually make it a tiny bit higher boiling or a tiny bit higher melting point than something like this. So think like a test writer. What kind of question could show up from number 2 on the test? It wouldn't necessarily be what's the lowest boiling point, but they could ask what is the highest boiling point, right? And of those, which one of these would you choose to be the highest boiling point? probably this guy right here because it has the most electrons and obviously the most surface area too. Okay, is that good enough for number 2?
Yep.
All right, number 3 then, which of the following has the highest melting point? So we have similar choices right here, and so the highest melting point would be the one that has the strongest intermolecular forces, and the strongest intermolecular forces would be the one with the most electrons, so that would be letter C. Number 4, the main forces responsible for binding copper atoms to one another in solid copper. So you need to look on your periodic table and what kind of substance is copper?
Transition. A metal.
Hopefully you said that copper's a metal, and metals, remember, are the ones that are, on this side of the periodic table all over here, and not including hydrogen. And metals are held together by what are called metallic bonds. Metallic bonds, remember, are characterized by electrons that are like delocalized, they call it, and those delocalized electrons are good at conducting electricity. And so you'd say metallic bonds, letter C right here. They could say that about any metal. Some people get confused because it'll be like, what holds potassium to potassiums? Well, potassium's a metal, so what would the answer be? It's called metallic bonds. So don't think too hard on those. Number 5, crystalline solids. Are crystalline solids usually very soft? No, they're usually very hard and brittle. Do they have particles arranged randomly? No, crystalline solid. A crystal means that it's arranged in like a crystal lattice, like very organized and very regular. They have highly ordered structures. That's true. Highly organized structures, they form a very regular organized structure. They exist only at high temperatures. That's not necessarily true. Crystalline solid could be water, I guess, because it's very organized, and that's not that high a temperature. Exist only at very low temperatures. Well, that's not necessarily true either, because diamond doesn't melt until over 2,000 degrees, and that's a very good crystalline structure. So they have highly ordered structures. Number 6, an amorphous solid. Amorphous solids are solids that are particles arranged randomly, but they're still they're still solids. And the other parts aren't necessarily true, they're just randomly arranged. Going to the next page. Which of the following has the highest boiling point? So the highest boiling point, remember, is the one that sticks together the best. Sticking together the best means that it would have things like hydrogen bonding, have lots of electrons, have dipole-dipole forces, have lots of London dispersion forces, and that goes right along with lots of electrons. So if you look at these choices right here, there's one of them, letter E, that has an OH, an H connected to an FO or N. Letter D has an H connected to an FO or N. And so either D or E would be your ones that have hydrogen bonding. And when you can choose between those two, you'd want to choose the one that has the most electrons. And I think letter E right here has an extra carbon. 1, 2, 3, 4. 1, 2, 3, 4, 5. This one has 5 carbons, so you're going to get more electrons in that one. So letter E is your best choice. More electrons, more London dispersion forces. Does that make sense?
Yep.
Okay, thank you for the feedback. Number 8, based on the figure above, the boiling point of diethyl ether under external conditions. So diethyl ether is right here. Pressure is 1.32 atmospheres. So you have to take the atmospheres and you have to convert that to torrs. So in 1 atmosphere there are 760 torr. And I think that data is given to you on the front of the test. I think they give you here that torr is equal, 760 torr is equal to 1 atmosphere. That's kind of fuzzy, but you can look that up. So you do that conversion, and so you end up with, what does it turn out to be? About 1,000 torr? Is that true? 1,000 and what? 32? So a little over 1,000, which means you're going to be way up here. And then you follow over to here, and it goes at about 40 degrees, and it says approximately. So I think the closest it's going to be is probably this 40 degrees right here, where it's going to match the line. Based on the figure above, the normal boiling point of ethyl alcohol. So the word normal means that it's at standard atmospheric pressure. Standard atmospheric pressure is about 760 torr, or 760 mummy hugs. And so the normal boiling point of ethyl alcohol would be to follow this across until it intersects with the ethyl alcohol. And look at that, it's even right there on the graph. It's 78.3, which is closest to 80 degrees right here. Based on the figure above, the vapor pressure of water in torr at 70 degrees. So 70 degrees Celsius is right about here. And the vapor pressure of water would be about right here on the line. So that's a little more than 200. So approximately 200, I guess, if you're given that choice, because it's closer to 200 than it is to 300. Questions on those? And then going on to number 11. CO2 does not exist in a liquid phase at normal atmospheric pressure. What does this imply about its phase diagram? And carbon dioxide, remember, at normal atmospheric pressure changes directly from a solid to a gas. Some people give that phase change name sublimation. And so what does it tell you about the phase diagram? Well, that means that it couldn't change to a liquid at 1 atmosphere of pressure, and therefore its triple point would have to be above 1 atmosphere of pressure, because it couldn't change to a gas. Couldn't change to a liquid during that time. So if you remember what a phase diagram looks like, remember it goes up like this, and then there's a triple point, and then from here it changes to solid, liquid, and gas. And so this is where normal atmospheric pressure is for, or 1 atmosphere of pressure is for carbon dioxide. And so you'd see that the triple point has to be above that because it doesn't change to a liquid phase at all at 1 atmosphere of pressure. I think the triple point's actually at about 5 atmospheres of pressure for carbon dioxide. So if they said the pressure was like 10 atmospheres and gave you this, then eventually you could go through the liquid phase and then to the gas.
Are we just supposed to know this? Is it because like normal, like air is like 1, and so it's saying like you can't do it, like you can't have liquid at 1, so it must be greater than.
Yeah. So my audience has a really good question.
We have names.
So the carbon dioxide, how are you supposed to know this? Well, it tells you that it doesn't have a liquid phase. You don't need to note, like have that memorized. But you should know something about phase diagrams, and you should know that if it doesn't change to a liquid at this normal atmospheric pressure, then that means that the point, called the triple point, where solid, liquid, and gas exist at the same time, must be higher or above where that normal phase change from solid to liquid to gas normally occurs. So yes, you should know something about phase diagrams and kind of have a picture of one in your head. As a matter of fact, I know for a fact that there are several phase diagrams, not only on this test right here, here's an example of one right here, but on the actual test itself, there's several phase diagrams like this, and it asks you questions about like, where is the triple point? Where is the critical point? What happens at the triple point? What happens if the pressure is down here? What's the phase change that takes place? Things like that you should know. Did that answer your question?
Yeah.
Okay, number 12. As a gaseous element evaporates, the atoms become more separated, and they have blank attraction. They have less attraction for one another because, of course, we went from a liquid to a gas, and gases are the least attracted form of matter. So that would be letter B, I believe.
Yeah.
Which one of the following exhibits only dispersion forces? So dispersion forces, remember, happen between everything, but which ones have only dispersion forces? Well, remember, there's 3 kinds of forces in the world. Three intermolecular forces. London dispersion forces, dipole-dipole forces, and a special case of dipole-dipole forces called hydrogen bonds. These 2 forces only occur when the molecules are asymmetrical. Asymmetry means that when you cut them in half, they're not the same on both sides. And so what you want to find for one that has only dispersion forces is one that is perfectly symmetrical. And there actually happen to be 2 of them that are perfectly symmetrical once you draw the Lewis dot structures right here. Turns out to be letter D is perfectly symmetrical because C and C bond with the O like that. And then C10H22 is just a super long chain of 10 carbons. And then the hydrogens bond all around it. So when you cut it in half, it's the same on both sides. So both of those, notice it says more than one answer is possible. That will not be true on the actual exam, that there will be more than one possible. But here it is because it's a practice exam. But those two are perfectly symmetrical. The other ones, if you draw them, you'll find out are not perfectly symmetrical, and therefore they have dipole-dipole or hydrogen bonds. Number 14, which of the following exhibits dipole-dipole forces of attraction between the molecules? So dipole-dipole, remember, has to happen if there is asymmetry. So once again, you get the same choices right here. So the three that are asymmetrical are pH3, which would end up looking like this in just a rough Lewis dot structure. So you notice that with this unshared pair of electrons here, if you cut it in half like this, you'd end up with two hydrogens on one side, a hydrogen and an unshared pair on this side. So that's asymmetry. Let's see, this is a different one. This one would have symmetry, CCl4. HBr would not have symmetry, so those two right there would be asymmetrical and therefore would have dipole-dipole forces. Which one exhibits hydrogen bonding forces of attraction? More than one answer is possible. So remember, hydrogen bonding is a special case of dipole-dipole forces when you have an H connected to an F, an O, or an N inside the molecule. So don't choose one if it doesn't have F, O, or N in it. And the only ones that have F, O, or N in them are these three. And it turns out that the only one that has a hydrogen connected to an F, O, or N is letter C right here. Some people pick B, but be careful. If you have a carbon, remember it wants to form 4 bonds. And the four bonds it will form is 3 of them with hydrogen. I'm sorry, 3 with fluorine and 1 with hydrogen. And so there's no H connected to an F, O, or N. So watch your Lewis dot structure on that number 15. 16, when KCl dissolves in water, it gives you these 2 ions right here. Notice it has a plus and a minus. The force of attraction that exists between K plus and H2O. So this is an ion. And then H2O looks like this and has a special attraction for electrons this direction, and they give it a fancy name. They call this a dipole because it has 2 poles, a positive pole right here and a negative pole right here. And so it's called an ion to dipole attraction, letter D. This happens between all charged things and water, and that's one of the main reasons lots of ionic compounds dissolve in water. Number 14, when decane dissolves in hexane, the forces of attraction that exist between the 2 molecules are called. So once again, draw the Lewis dot structure if you're not sure, and you can draw a rough draft, and this would have 10 carbons. I'm not going to draw them all right here for C10H22, and it would be very regular, very ordinary, very non-polar because it's perfectly symmetrical. C6H14, same thing, except it's only 6 carbons in a row. So what kind of forces exist in each of these? Obviously, there's no dipoles, therefore there's no H, and there's no H's connected to F, O, or N's, so those 2 kinds of forces are out. The only other kind of force that exists are London dispersion forces. So those have to be the ones that dissolve or attract each other. And remember, like dissolves like, so since this one has LDFs and this one has LDFs, well, there they go, LDF together. Which of the following derivatives of ethane has the lowest boiling point? So lowest boiling point would mean that it sticks together the least. That means it has the weakest intermolecular forces. So you're looking for something with maybe only London dispersion forces. No dipole-dipole, no H to F, O, or N. And so if you look at each of these and draw the Lewis dot structure, you'll notice there's 2 carbons. Remember, put carbon in the middle if you can. And then for all the other ones, there's 6 of the other items. So there's going to be 6 things bonded around the carbons here. You either have the choice of H's all around here, Cl's all around here, I's all around here, F's, or Br's all around here. Notice that if they're all the same thing all around here, whether it be H's, I's, F's, or Cl's, they're all going to end up being perfectly symmetrical, which means the only kind of forces between all 5 of these kind of molecules are called London dispersion forces. What makes London dispersion forces strong? Lots and lots of electrons, right? So which one's going to have the most electrons? Well, you got to look at fluorine, chlorine, bromine, and iodine, and hydrogen, and decide who's got the least electrons. Turns out hydrogen has the least number of electrons, so C2H6, letter E right here. How are we doing so far? Following along?
Yep.
Pretty good? Okay, number 19. The property responsible for the beating up of water. I think this is because water adheres to itself really good, and since it adheres to itself, it forms like bubbles that would bead up, and so H2Os would connect inside to other H2Os. Some people say that on the surface right here, then the water experiences a tension, and this tension is called surface tension to make it stick together really, really good. Of the following, blank is an endothermic process. So endothermic means energy has to go into the system. And so the system you could think of as being like water, because water can undergo all of these different things. Which one do you have to put energy into to make it happen? So, for example, going from liquid to gas is called boiling, and to do that you would have to add energy to the liquid to make it become a gas and separate the particles. So boiling would be an example of an endothermic process because energy has to go in. Evaporation would be another example because you're going from a liquid to a gas once again. Subliming would be another one where you would have to put energy into the solid to make it go to a gas. Melting would be another one because you'd put energy into the solid H2O to make it go to a liquid. Freezing would be exothermic though, because you'd go from a liquid to a solid and you let energy off to make it go from a liquid to the more stable solid state. Of the following, blank is an exothermic process, so you get almost the same choices right here. Exothermic means energy is given off, and so I think freezing is my one answer right here because I'm going from a liquid to a solid. Deposition would be another one that would be an exothermic process because you're going from a gas to a solid right here. So you'd have to give off lots of energy to make it slow down from being really bouncy around gases to a very organized solid shape. So those two would be exothermic processes. Brass. Brass is a mixture of copper and zinc. It's called an alloy. How do you remember that? B-R-A-S-S. S looks kind of like a backwards Z, so you can remember it's zinc, and then brass looks coppery color, so it's copper and zinc put together. Chrome is an iron and chromium. That's why it's called chrome. Chrome and iron. One of these two is on the test. I can't remember which one. So 2 things to memorize, I guess, as far as alloys go. Which of the following substances does not have hydrogen bonding? So remember, hydrogen bonding has an F, O, or N connected to an H. And in this one right here, we do not have an F, O, or N connected to an H. Backside right here, we have, based on the following information, which has the weakest intermolecular forces. Argon right here would have the weakest because it has the lowest energy of vaporization. It takes the least amount of energy to make it go from a liquid to a gas. Phase diagram questions. There's a lot of these on the test. I think there's 7 phase diagram questions on there. So blank segment corresponds to the conditions of temperature and pressure where the solid and liquid of the substance are at equilibrium. Remember, this is solid, this is liquid, this is gas. That's true of all phase diagrams. And so where is the solid and the liquid in equilibrium? Between here and here. So that would be A to D, which is letter C right here. The next one, on the phase diagram, the coordinates of point blank correspond to the critical temperature. B right here is the critical temperature. Above that temperature, you no matter how much you compress it, you can't make it liquid anymore. It becomes what's called a supercritical fluid, and it's just the point at which no more pressure will make a difference. On the phase diagram shown above, the coordinate points of blank correspond to the triple point, and I believe the triple point's right here. Is that an A? I think so. That's an A. On the phase diagram above, segment blank corresponds to the condition of temperature and pressure under the liquid and gas of the substance are at equilibrium. So that would be right between here and here. So that's A to B. So A, B is letter A. The concentration of chloride ion in the solution contains 0.9 calcium chloride is, okay, so we're done with phase diagram questions now. We're moving on to a concentration. So calcium chloride, this is a trick question because the formula for calcium chloride is CaCl2, and the concentration of chloride solution that contains 0.9 molar calcium chloride. If this is 0.9 molar, now look at the formula carefully. How many chlorines are inside of this formula? 2. So inside of this formula there are 2 chloride ions for every complete calcium chloride. So 0.9 times 2 is 1.8, so it would be 1.8 molar in terms of chloride ion. I don't think there's a question like that on the test. There are questions about molarity on there, but not like numbers on there. The concentration of a nitrate ion contains 0.9 gallium nitrate. I believe gallium nitrate is GaNO3,3. So then they trick you again by saying this whole thing is 0.9. Just like this last one, what would be the concentration of the NO3s in there then? 3 times 0.9 is 27 or 2.7, right? 2.7. And like I said, I don't think there's one on the test like that. Concentration of urea in a solution with 30 grams of urea and 27 grams of H2O is percent by mass. So percent by mass would just be taking the mass of the part, 30 grams, divided by the whole thing. So you have to add 72 and 30 together, which I believe is 102, and then multiply that by 100. So 30 divided by 102 times 100 turns out to be, well, it's pretty close to 30%. It's a little bit off. 29.4, thank you. And then the concentration of urea in a solution is of 10 grams and 36 grams of water. So same kind of question, except for it's 10 divided by 46 total times 100. 10 divided by 46 is, did you say 21? 27%? 21.7%. So that's part divided by whole. We're getting close. The phrase like dissolve like refers to the fact that polar solvents dissolve polar solutes and non-polar solvents dissolve non-polar solutes. So that's what like dissolves like mean. Supersaturated solution is one with a higher concentration than solubility normally says is possible. Saturated solution contains solute in equilibrium with undissolved solute. It contains as much solvent as it could hold. Not necessarily. It's usually, it contains as much solute as it can hold. I think that's the trick part, is that there's a V there. Cannot be obtained conditional double bonds. I think C is the right answer there. It contains dissolved solute in equilibrium with undissolved solute. Yeah, I guess it could be that, or it could be A right here. The bottom line is a saturated solution. If you have a solution in a beaker right here, and you dissolve like a solid inside of this, let's say it's H2O, there's a certain amount that will dissolve. And when you have as much as possible dissolved, then this liquid portion right here is called saturated. Now it could happen that you put more solid in there, so it's saturated already, and some of the solid sits on the bottom. This liquid part of this solution right here is still a saturated solution, and so C would be true at that case, where there would be some solute sitting at the bottom, and it's in equilibrium with the undissolved solute, where some of it would be dissolving and some of it would be precipitating all at the same time. But that's not necessarily the only time it's saturated. You could have exactly as much dissolved in it where no more would dissolve at all, and so it's not the best question. Number 37, a solution is made from 10 grams of sodium chloride, 5 grams of potassium nitrate, and 100 grams of water. What is the mass percent of sodium chloride in the solution? So sodium chloride is 10 grams. You have to divide it by the whole thing then. So 10 plus 100 plus 5 is 115. So 10 divided by 115 times 100%. It's going to be 8.6 something percent. Close enough. Let's see, a solution is made of 20 grams of potassium chloride, 25 of sodium nitrate, and 100. Same kind of problem, except this time it's asking for the mass percent of sodium nitrate. So sodium nitrate would be 25 grams divided by the whole thing, which is 100 plus 20 plus 25, which is 145 grams times 100. And this is 17 or so percent, plus or minus a little bit. Which of the following statements is false? This is true that the solubility of gases decreases with increasing temperature. That's true. Non-polar liquids tend to be insoluble in polar liquids. That's true because like dissolves like. Letter C, the weaker the attraction between the solute and solvent molecules, the greater the solubility. That's not true. It's the stronger. Oh, so that would be false. Okay, because it asks which one's false. The solubility of a gas increases in direct proportional to its partial pressure above the solution. Yeah, if you put more pressure on the gas, more will dissolve. And letter E, substances with similar intermolecular attractive forces tend to be dissolving in one another or soluble in one another. That's true because like dissolves like. So C is your false one. Pressure has a large effect on solubility of gases in liquids, right? So when you're dissolving a gas in a liquid, if you pressurize it a lot will dissolve. 41, a solution contains 18% phosphoric acid by mass. That means that there are 18 grams of phosphoric acid in the total of 100 grams of solution. And so 100 grams of this solution contains 18 grams of phosphoric acid, letter B. Now we've got some math problems here. How many moles of nitric acid are there present in 300 milliliters of 2.6 molar HNO3? This one's a molarity triangle problem, so molarity equals moles divided by liters, and it asks how many moles are there, so moles are equal to our molarity, 2.6 molar, times our liters, 0.3 liters, multiply those two animals together, and then you get the number of moles.
Do you want us to know?
Sure, what is it?
0.78.
0.78 moles, thank you. And 43, how many moles of nitric acid are present in? So same kind of question, except for this time it's 0.6 molar times 0.5 liters. Does that turn out to be 0.3?
Yep.
So that's number 43. And then number 44, a sample of water has an oxygen concentration of, what is the oxygen concentration in parts per million? Assume that the density is pure water. So we have a 2.36 times 10 to the, I believe that says -4th moles per 1 liter of solution. Remember, you can rewrite molarity as moles per liter. So it tells us that it happens to be oxygen in there, and oxygen is written as O2. And remember, to find parts per million or parts per billion, it's always just like percent, where we'll take our grams, divide it by grams, and then we'll multiply it by a million. So what I need to find is the grams of O2 in there, the grams of my solution, which it gives me a big hint right here. It tells me the density is 1 gram per milliliter. And then I divide those two and multiply by a million. So let's convert from moles to grams. Put moles in a position of it where it's going to cancel. Grams of O2 in my new set of units. 32 grams in a mole. So if somebody wouldn't mind taking 2.36 times 10 to the -4th and multiplying it by 32, I'll fill that in right here for grams of O2.
0.07552.
0.07552, is that what you got?
Yep.
Okay, so there's our grams of oxygen. And then we have 1 liter of